So welcome back again, guys. The last episode we were learning about the photoelectric equation by Einstein Albert Einstein. So the equation looked like this. So before going into the equation, let me just show you what the physical process that was happening over there. Suppose you had some metal. Okay, this is just a simple picture. It's a very simple picture. I am making it way simpler to get you an understanding of the concept of what photoelectric equation actually means. Suppose you had a metal piece, we call it metal A. Okay, you can call it metal A. Now you had an electron. I mean, obviously there is a sea of electron in this metal, but just consider a single electron. Okay, now you must listen to this part very carefully, because this will give you the difference between the classical picture of radiation as well as the quantum picture of radiation. I mean, we are studying the chapter at present is about the dual nature of matter and radiation, and first part of which is actually the dual nature of radiation. So in the previous chapter we studied that light is made of waves, or light is actually some sort of waves. So not made of, but you should say it's some sort of some sort of waves. In fact, indeed, it was later found out that it was waves in the electromagnetic field, so that's why they were also called the electromagnetic waves. Light propagates as disturbances in the electromagnetic field, and those waves are called electromagnetic waves. And this was a well established experimental as well as theoretical research that went on for around 100 years, since the time of Gauss to Maxwell. So Maxwell was the person who conceived the concept that light might indeed be electromagnetic waves, and later was experimentally verified by Hertz that light is indeed electromagnetic waves. But accidentally, during the experiment where Maxwell was further performing advanced experiments based on electromagnetic waves, in the same experiment he discovered the photoelectric effect. It's a sort of like irony, like the same person proves that light is waves, as well as the same person paves path to the concept of the particle nature of light also. So it's Hertz who has been the cornerstone of all this research. So an appreciation for that great scientist. So okay, let us come back. Let us keep this history aside. Let's move on to this. There is a metal A, and there is an electron. Consider one electron. Okay, even considering an electron as a point is a mistake, but meanwhile, as far as what we know is that they are particles. They occupy a particular position in space and can be pinpointed out. So that is what particle means. Now, light is photon. Okay, light is photon. So light is light is composed of quantum of energy. Light is composed of quantum of energy, and they are not continuous. See, if it were continuous, something odd would have happened. What? Let us see what would have happened. See, if light were continuous, and continuous means, see, if this photon is sitting there, and it needs some energy to get out from that particular configuration of its. Okay, so it wants some energy to escape that particular configuration. Now if light were continuous, you would have supplied energy continuously. See, according to the classical theory, each of this wave amplitude contains energy. So you have like you have this wave has some energy, this wave has some energy, this part of the wave has energy, this part of the wave has energy. Everywhere continuously there is energy and is proportional to the amplitude of the wave at that point, square of the amplitude of the wave at that point, which is intensity obviously. That is, energy according to the classical theory is proportional to the intensity of the wave, and everywhere in space there is some intensity associated with the wave. So which means it's a continuous thing. Okay, from here to here you have energy. Now if this electron needs to escape from that point, and if that was the case, you could have just supplied energy continuously. Okay, for example, okay, let me just go on further. Okay, so if this electron, suppose this electron required, say for example, it required 3 joules of energy, okay, and the incoming radiation suppose you use some blue light. Okay, you use a blue light. Now the incoming radiation has energy density, which is energy density per unit time, or the power transmitted just in 1 second would be, say, the amount of energy transmitted, the power of the wave, amount of energy transmitted by the wave in 1 second in unit time, or 1 second, was, say, equal to I just have a good number. Okay, let me just, for the sake of calculation, let me make this 100 joules, and energy supplied by the our radiation was, say, 2 joules per second. So if that was the case and it was continuous, then this electron could have absorbed the could have waited there as long as, like, how many seconds for the electron to consume. Since the energy is coming continuously, it seems like the electron should wait there long enough to get 100 joules, right? That's what it seems like. So 2 joules per second was the energy that this radiation supplied in 1 second, which means for 100 joules it would have required 2 times some number y is equal to 100 joules. So y would be equal to 100 joules by 2 joules per second, and this gives you a value of 50 seconds. So if the electron remained there for 50 seconds and the energy was continuous applied to the electron, that electron would have jumped. Okay, but that does not happens. This is where the concept of threshold frequency beats all this. Threshold frequency. What is threshold frequency? I have told you, I have discussed with you what threshold frequency is. So any wave with frequency below the threshold frequency cannot, I mean, using the term push is a very wrong, illiterate thing, but still, for the sake of simplicity, we can say push. It cannot push the electron out of its sight. Okay, so however long it waits, however long the radiation is supplied, okay, the supply of radiation is there. So this is a very crucial point, which means if you have some radiation with frequency, if you had some radiation with frequency less than the so-called threshold frequency, this radiation, however, like, even if it's applied like 50 joules per second, it cannot push the electron, which required like exactly 100 joules energy to get out from the lattice site. Okay, this, however long you waited, this cannot provide the push. So exactly you required a radiation which could supply like 100 joules in just 1 second. Not even 1 second. Albert Einstein said it is not even 1 second. The amount of time it takes is infinitely small. And that's all for now, guys.